Hi everyone, this is Iman and welcome back. In today's video, I'm going to talk about something that's often overlooked in structural design, and that's thermal loads. Even under normal climate conditions, whether in summer or winter, temperature changes can play an important role in a structural design. If we don't account for them properly, they can lead to cracking, serviceability issues, or even overstress in certain members. Let's get to it. All right, a quick introduction about our discussion. So you can see a plan view right here, and typically in buildings with large plan dimensions, thermal analysis can become important. So that's why, as a rule of thumb, in long buildings, we usually provide expansion joints, typically every 100 feet or about 30 meters. Okay. So these joints, you can see here in this picture, separate the building into smaller segments so that thermal expansion doesn't create large stresses or forces or deformations. Okay? But what if expansion joints are not possible? In that case, the structure itself must be designed for thermal loads. And that's where the fundamental formula comes in. Delta L equals alpha L delta T. It's simple but powerful. It tells us how much expansion or contraction occurs based on the alpha, which is the coefficient of thermal expansion, L, the length of the structure, and delta T, which is the temperature change. Okay? And of course, knowing the elongation alone isn't enough, right? We need to make sure thermal effects are part of our basically design load combinations. For example, ASCE 7 provides two load combinations that specifically include thermal loads. Okay, you can see here T is the temperature. Okay. All right. Now let's connect this to practice. In ETABS, the workflow is pretty straightforward. First, we define alpha. And according to ASCE, for steel, alpha is about 6.5 times 10 to the minus 6 per degree Fahrenheit. And if you're using metric or SI units, this value is for SI unit per degree Celsius. Okay, and for normal weight concrete, it's alpha is 6 times 10 to the minus 6 per degree Fahrenheit. Okay, and if you have a lightweight concrete material, you can use this value. All right, then we define load combinations per ASCE 7, these two combos. Okay, next we assign delta T. Okay, and again, according to ASCE, delta T depends on both climate and material. So for this example, we'll assume delta T is about 85 degrees Fahrenheit, or it's 30 degrees Celsius. And next, this is really important. We have to make sure the diaphragm is set to semi-rigid. If the diagram is modeled as rigid, ETABS won't be able to consider thermal effects, because a rigid diaphragm assumes zero in-plane strain, and that also means zero thermal strain. Okay, and finally, make sure to include thermal case in your design load combinations. All right, let's jump into the ETABS and set it up step by step. All right, I've got a model here with a very long plan dimension, which makes it a good example for studying thermal effects. Okay. All right, first I'm gonna define alpha, define material properties, and this is steel properties, and over here alpha is over there, okay, which is exactly the same value that ASCE recommends. Okay, perfect. And so I don't need to change this for steel. Let's take a look at concrete. It's 5.5 and ASCE says it's 6. It's very close, so you really don't need to change it, but if you want, you can apply this value. Okay, and again, I'm using Imperial English unit. So if you're using Celsius, make sure to use the correct value over here. Okay, so okay, all right, first step is done. Now I'm gonna define load combinations in ETABS. To do this, I need to define a new load pattern. These are my existing load cases, so I'm gonna define a new load pattern, call it temp, which stands for temperature. Okay, and then I go to define load combinations, and these are my current load combinations: gravity, lateral, seismic. So now I am going to add a new load combinations. I'm going to call it T1, for example, for temperature or thermal 1, and according to ASCE 7, it's 1.2 dead. Also, I have super dead, so it's same factor, plus 0.5 live load, plus 5, sorry, this is load, live roof, 0.5, plus 1.2 temperature. Okay. All right, this is T1. Now I'm gonna copy this and call it T2, and this time instead of LR, I'm gonna consider a snow load with the same factor. Snow. Okay. Okay, perfect. Now the second load combinations here over here. T is here with factor 1. So I am going to copy this, call it T3. This time live load has a factor of 1.6 and 1.6. And for temperature, the scale factor is 1. Okay. Hit OK. Now copy this, T4. And this time I'm gonna switch it to a snow. Okay, great. These are 4 load combinations that account for thermal analysis. Okay, perfect. So step 2 done. Now we're gonna assign a delta T to our members. So I go to select object type, all linear members, columns, beams, braces, select, and then go to assign frame loads temperature, and load pattern name is temp. And as I mentioned earlier, in this example I'm going to apply 85 degrees Fahrenheit, which is about 30 degrees Celsius. Okay, so hit OK. Okay, great. Now I'm gonna select my slab, which is over here. Floors. Now I go to assign shell loads temperature, temp, and again 85. And if you have shear walls, again do the same process. Okay, so we have to make sure all members are under thermal loads. Okay, go back to our notes. Okay, this step's done. Now the next step is really important. Make sure don't miss it. So we're gonna assign a semi-rigid diaphragm to our slab. So I'm gonna select my slab, go to assign shell diaphragms D1, modify D1, modify, and make sure to select semi-rigid option. Okay, okay, and okay. Okay, great. Next, make sure that we have our thermal combinations in our design load combinations. So if I go here, for example, if this is a steel frame or a steel structure, I go to design, steel, and steel design combinations. And you can see here, these 4 load combinations should be added to our existing load combinations. Okay, okay. And that's it. We need to run the analysis and let's see what happens. Okay, great. Now I'm gonna design the model. Okay, done. Okay, cool. Okay, let me zoom in a little bit. For example, for this column, I'm gonna right click over here. You can see the design check results for this column shows among all load combinations, including seismic ones, the governing case is actually the temperature load combination, T2. It's really interesting, right? That's why it's so important to always include thermal load effects in your design. Okay? And all right, and one quick note about concrete beams. Let me show you real quick. Concrete beam. All right, so to capture the axial force from temperature in reinforced concrete beams, we need to treat those beams as columns, because as you can see here, the default for design of reinforced concrete beams is moment only. Okay, so if you have a concrete beam, make sure to unlock the model and then select the first option. That way you can add P or axial load. Otherwise, ETABS won't be able to capture the axial deformations as a result of temperature elongation. Okay, and remember, temperature changes create axial stresses or forces in members, and that's why we have to account for that in our design. Thanks for watching. That's it for today's video on thermal loads. If you found this helpful, don't forget to like and subscribe to support the channel. Thank you.